if you look at a point on here, that point is coming down, touching, and then moving up again, and then touching, and then moving up again, like that. So that would be a specific point here. The friction is acting this way, but the movement is towards here, is coming at the surface, and then coming off the surface. So the friction actually doesn't do any work. Normal force, it does, there is some slight movement in the direction of the normal force here, but that normal force is only being applied at that brief moment. It just touches briefly and moves on. So this isn't doing any work either, because that normal force is being applied at the point that moves. Basically, as soon as that point moves, it's no longer touching the surface. Normal force isn't being applied anymore to it. So the only force doing any work here is the weight. Therefore, energy is conserved. I have two types, kinetic plus potential. I do have two kinetic energies to worry about because it is moving in it, the center is moving in a straight line, and at the same time it is rolling. So I have the translational kinetic, and then I have the rotational kinetic, and then potential energy because I have conservative force there. That's initial. So if I start them at rest, which of these are going to be equal to 0?
Both the kinetics,
Okay.
both the initial kinetics.
Yeah, there we go. Because V initial is equal to 0 and omega initial is equal to 0. That would be radians per second. Anything else going to be equal to 0?
The final potential,
Why?
because it's at the bottom of the ramp. Because I said so.
Yes, there we go. You can set potential to be 0 wherever is convenient, and so apparently Chloe wants to set it there. All right, so we're left with, what's the formula for this, for the gravitational potential energy associated with weight?
MGH.
And formula for translational kinetic energy?
Not one
Squared.
There was a lack of enthusiasm in that one. That was final squared. And the formula for rotational kinetic energy?
1/2 I omega squared.
There we go. And it sounded like a single voice. That's how perfect that you were in unison. All right. So it comes down to the initial potential energy is equal to the final kinetic energy because Coy set it up for that to happen.
Is rotational not 1/2 I omega squared?
Oh, it is. Is that what you said? Right?
Yeah.
Thank you. All right, so let's start. We can't get rid of anything at this point, but there is a formula for I. So if we're doing the solid ball, we get mgh initial is equal to 1/2 mv final squared plus 1/2 times, what's the formula for the moment of inertia of a solid sphere?
2/5 mr squared.
I now have mass across the board. I have 3 terms here. Mass is a factor in all of them, so that can cancel out. I can divide out the mass. And now I've got R omega. What is R omega?
V squared.
R squared and maybe squared, yes. So I have GHI is equal to 1/2 V final squared plus 1/5 V final squared. So that's 7/10 V final squared. And so my final speed is equal to the square root of 10/7 GHI. All right. A critical thing here, in our nice ideal, no slipping, rolling going on, is that the mass of the object does not show up in the final equation, and the radius of the object does not show up in the final equation. These moments of inertia do depend upon the mass and the radius. But just looking at this and going, oh, this has the largest moment of inertia, therefore it will be the slowest at the bottom, is not the actual way to look at it. It's a much larger radius, so it doesn't have to roll as much. So, what is the big factor here that is going to affect how fast it's going to get down to the bottom?
Height.
The height's the same for all three of them, so that's not going to be a discriminating factor
Is
here.
it the fraction in front of that one?
Yes. That number right there and apply 1. That number right there is the one that will decide. The solid ball has the smallest fraction there. It will get down first. The hoop will get down last. From an energy point of view, that fraction shows up right there. The bigger the fraction is, the more of the energy. Think about it, I've got a store of energy to start with, my potential energy. It starts to roll down. Some of the energy goes into getting it to move. Some of it goes into getting it to rotate. The bigger the fraction, the more energy that's required, a higher percentage of the energy required to get it to rotate. Therefore, there's less translational kinetic energy, there's less energy to get it to actually move down the ramp. So this requires a higher percentage of the energy to rotate. This requires the least amount of energy to rotate. Therefore, more is left over to get it to move.
Can you explain that again? So the bottom one is the least?
Least. Because even if all the masses in ours are the same, well, actually, the mass of the object and the radius of the object canceled out. So that actually doesn't matter. The one part of this formula that survived is this fraction up front.
So the top one is the most, no, the middle one is the most?
That's the smallest fraction.
Okay.
So, which means that from an energy point of view, the lower this fraction is, the less energy is, a smaller percentage of the energy is required to get it to rotate. Which means more energy is left over to get it to actually move down the ramp.
So, in other words, the solid ball would roll to the bottom of the rim first?
Solid ball would get there first.
Okay.
And we can demonstrate it some here.
It's gonna make it better, it requires less energy than the other ones.
All right, hoop and ball. The ball definitely weighs more than the hoop does. And it got there first.
Makes sense.
If we did solid disc and hoop, which would get there first?
The solid.
Why? Why is it gonna require less energy?
That I can't answer, I just have a feeling. Well,
Well, your feeling is correct.
Because it just is 1/2 M1 squared.
Yeah, all right, so from the math point of view, formula is 1/2 mr squared, this is mr squared. From a slightly different point of view, all of this, if it's rotating about the center here, all of this has to get rotated about it. It's all going sort of that same speed as this part right here. This has more mass in the middle, which doesn't really go very fast in the rotation. And I'm assuming that you can see that. And then to show that the size does not matter. And apparently it did just then. Did like that. That was a better one. Ignore the demonstrations that don't work.
Just drop it down the videos.
And then we have small ball and large ball. These should get down at the same time.
you're saying they're gonna get down at the same time because they each require the same amount of energy despite their size?
They each require the same percentage of energy. This is gonna have more potential energy to start with than this will.
Because of weight?
Yeah. But percentage wise, it's gonna still needs the same amount.
So, if you put like a boulder, a perfectly sphere and a marble on a ramp, will they roll down at the same time?
They should.
Okay.
Now, we can interject some reality into it. I don't know if you want to or not.
Wasn't really the point of my question.
Okay. In a nice ideal situation, absolutely.
Like in a vacuum, that's how it would work. There's no air.
The other one is a boulder and a marble have different surfaces, and so the friction is gonna be a little bit different. So rolling friction would be a little bit different between the
We
two.
said if it was perfectly spherical, if the boulder.
Perfectly spherical is fine. It also assumes that whatever it's rolling down is perfectly rigid and that it won't, there are no micro flexing to make up a new word. All right, so that's number 2. And then the momentum equation, or the collision. Actually, let me jump to 4 first, and then we'll come back to 3. On number 4, that is, it's a thin-shelled sphere. So we're dealing with a hollow ball. So it's, the formula is 2/3 mr squared. So instead of 2/5 here, it's 2/3, which makes that 1/3, which makes it 1/2 of a third of 5/6. So number 7 is asking you to find V at the bottom. And so you go through the same process, just a different fraction here, and solve a V.
So wait, are we on number 4 or?
I skipped, yeah, I'm doing 4 just because this relates directly to it.
So it would just be that final equation of the 6 then.
So that would be 2/3, which makes this 1/3, which makes that 5/6. So that becomes 6/5. So 1.2 times 9.8 times that additional height. 10-meter long ramp. This angle is 36.8 something. 8698, blah, blah, blah. Degrees. In other words, the sine of that angle is 0.6. If I give you a long angle like that, either I was just being, it was my sense of humor when I was writing the test, or it's so that the sine and cosine come out to be really nice numbers. So this height here would be 6 meters. That's meters per second squared. And at that point, it's a calculator exercise. Now, let's just suppose you wanted to solve it without using energy, because you are a masochist. You can consider the weight acting at the center here. It's basically pivoting about that point. So this weight right here is creating a torque about the pivot point here. You can figure out what that distance is. And therefore you can find the torque of the wheel, with R cross F. So R would be that vector. The force is weight. Find the torque, and that's going to be equal to I alpha. The normal force and the friction force exert no torque about that contact point. And so we know that we can find the angular acceleration. Once we have the angular acceleration, we can then find the linear acceleration. And then once we have that, we can then calculate how long it takes to go down. That's if you want to do it the harder way.
Easy way me please.
Say again?
Said easy way me please.
I have had a student actually do it this way instead of the energy way, but he did it correctly. More power to him. All right, number 3. Just standard, perfectly inelastic. I even specifically said they stick together, although I would hope that you would know that, because I don't always state that they stick together. We have a 7 kilogram mass. Moving at 4 meters per second along a frictionless floor. And then we have, it would have been more interesting if the 11 kilogram mass had been moving. Oh well. Velocities of the masses after the collision, if it's perfectly inelastic. So they're going to stick together. I could have worded it, what's the velocity of the mass afterwards for part A. But I guess I just wanted to keep it generic. They will have the same velocity afterwards. They stick together. There's no way one will be traveling faster than the other, unless I throw in a rotational aspect to it, which I'm not. So P initial is equal to P final. 28 is equal to 18 V final. 1.4 repeating meters per second. I don't think I made the Carroll's error.
Is that 1.4 repeating?
Yeah, it should be 1.5 repeating. I did make the Carroll's error. The second one is the more interesting problem in my mind. The perfectly elastic collision. We've got the three techniques. Now, I will tell you, some people in the master set, and was not forbidden on the master set, but some people in the master set used a formula for, given the masses and the inertial velocities, it just straight plug and chug. That will not be given to you. If you'll notice on the sheet, that formula is not given to you. If you don't know what formula I'm talking about, that's fine, because you don't need to know it. However, you do need to know which technique you're going to be doing, the first, second, or third one. I think the last time I did one of these, I did technique number 2. So how about I do 1 or 3? 1 is, we'll get to a quadratic, but one of our answers will be 4 meters per second and 0 meters per second, the non-collision solution, or the one passes through the other. So, and the other one is center of mass.
Will we be given the relative speed of approach formula and relative speed of recession formula? It might be on here, I don't see it on this one.
Oh, I don't have chapter 7 equations on here. I'm missing, oh, there's the momentum stuff, okay. Oh, I need to redo the chapter numbers, that's part of the problem.
That used to be chapter 10.
I think these are the chapters that, from the 251 book. That's what I get for cutting and pasting. Oh, there we go. Yeah, I'll give you, let's see, so V1 initial minus V2 initial equals V2 final minus V1 final. So I will add on there V1 initial minus V2 initial